Are we taking classroom lecture or what? Means offline mode. So, but it is not mandatory for mechanical, right?
I
Is
mean,
it?
sir, we do not know. Like, it was told that for those in campus, there may be offline class, and for those who are at home still, they'll have to avail online class till they come back to campus.
But that is for certain 4 branches, I think so. Is it? We have received mail that will be implemented for 4 branches, 4 different branches. But mechanical is not included in that, I think so.
So we don't know about that. Like the mail that
Okay,
which we
that is
received
okay.
said that all second year students in campus have to attend offline classes.
That is okay. So what about other classes, other subjects of yours? Have you
Other
attended?
subjects are taking offline, sir, as far as I'm aware. Like we had a class just before this on basic electronics, and that was in offline mode for the people in campus.
Okay, electronics is electronic subject. Okay, any mechanical subject?
Uh, Today we haven't had another mechanical subject other than this.
Okay, okay, okay. Fine, fine. I'll find out and then I'll see what is the possibility and all. So for today and Friday, let's continue like this. Okay.
Okay, sir.
Okay. Thank you. Thanks a lot. So in our previous class, we have discussed very well about Rankine power cycle. In that, we have seen what are the 4 processes involved, and also we have seen what is the possibility to improve or enhance the efficiency of the Rankine power cycle. So in that scenario, we have seen reheating, that is one concept in the turbine side, and regeneration, that is one concept at the pump side. These two we have implemented, and then we have seen different other things like how it is deviating, what are the reasons for the ideal cycle is deviating towards the actual cycle. Okay. So today, let us discuss about refrigeration cycles. Okay. So in these, whatever the refrigeration cycles we are discussing in this, those also phase change kind of refrigeration cycles. So let us see here that we can call vapor compression refrigeration cycle. Okay. So this is the refrigeration cycle we have here. This is applicable to your refrigerator, whatever you have at your home, and also your air conditioner. Okay, that could be window air conditioner or otherwise a split AC. Okay, anything working upon this particular principle. What is happening over here? If you see saturated vapor of the refrigerant, okay, saturated vapor of the refrigerant is entering over here in the compressor. That is compressing to high pressure. Since it is the vapor, its temperature also increasing. Okay, then that high temperature, high pressure vapor is reaching to the condenser over here. In the condenser, certain amount of heat is rejected. Okay, then the name itself is saying condenser. Is it? Again here, phase change happening over here. Okay, the gas at a high temperature and high pressure is coming over here as the liquid, saturated liquid. Okay, then after here we have one valve. Okay, so here we are expanding it. Okay, because of that, what is happening? Because of the expansion, its temperature is decreasing. Okay, its temperature is decreasing. Now we are passing such a low temperature liquid in this evaporator. Okay, in this evaporator, this is our domain, whatever we are looking for. This is your refrigeration cabinet where you are putting your food stuff, or this is your entire room where your AC system is blowing certain amount of air, cold air. Okay, that could be window AC or split AC. Okay, in case of split AC, these all components together, these 3 components. Okay, these 3 components together is in one box. That box you are installing outside. Only this guy, evaporator, you are putting inside the home. Okay, That is for the case of split AC. Okay. See here, nothing difference than your Rankine cycle. Okay. So this is also isentropic compression. Okay. This is constant pressure heat rejection. This is isentropic expansion, and this is constant pressure heat addition. Okay. Such a way. Only the difference is that whatever we have studied earlier, that was power cycle. This is the refrigeration cycle. Okay. That was delivering certain amount of work. This is consuming certain amount of work. Okay. So here, whatever expansion is there, so in case of Rankine power cycle, wherever you are expanding, you are used to get certain work. That is only shaft work you are getting. Then that work you will be connecting to the generator. That generator is producing electrical energy. The purpose of generator is to convert mechanical energy, which is the shaft rotating at high RPM. Okay. 2 pi nt by 6. Yes. T is the torque, N is number of rotations. Okay. That is giving you certain mechanical energy. That energy or power is converting to the electrical energy, that where we have generator. Okay. But here, in this case of refrigeration, whatever the expansion is taking place, okay, this is the liquid. There actually, in case of Rankine cycle, we have expanded gas. Okay, gas. That specific volume was very high. Okay, here this is the liquid. Still, this is also isentropic expansion we can consider, and even not isentropic, ideally. But since it is in the liquid phase, its specific volume is very less. The work, whatever is producing through this expansion process, is almost negligible. Okay, that's what we are not taking any work from this device. Okay, so this is the negligible work, so we are not taking. Only thing is we have to supply work over here. That is the reason this is the refrigeration cycle, which is taking the heat and sucking the heat from the low temperature and pushing it to high temperature. Yes. Okay. These are the similar kind of, but only thing is in case of Rankine cycle, you follow this way, okay, clockwise direction. Here you are following in anti-clockwise direction. Okay. Here, if you follow this thing only, 3, 2 dash, 1 dash, 4. This is again coming as Carnot cycle, is it? So I should not come this direction. I should go from this direction. 1 dash, 2 dash, 3, 4 dash, 1 dash. Okay, this direction now. Okay, this cycle is resembling like Carnot cycle. Then, what was the problem in case of your Rankine cycle? If you follow the Carnot cycle, the steam which was entering in the turbine was saturated steam. When you are expanding, okay, so much amount of moisture was there at the end of the turbine expansion. But we have one limitation, it should not exceed 10%. Okay, so that's what we have done. We have gone to the superheating that we have studied over there yesterday's class. The similar way here also, suppose see, what is this process over here? This is condensation process, this is throttling process, and this is the evaporation process in the evaporator. Okay, so suppose we are assuming 1 dash, 2 dash by adapting your compressor, then compressor has to compress two phase, means partially vapor and partially liquid. Okay, so but it is not possible to compress such a way. Okay, it is not possible to compress such a way. That is the reason. What are we doing? We are further going towards over here. We are making it is at least saturated. means liquid over here, and then means vapor over here, and then we are compressing it. Okay, so that is the reason in both cases, even in case of refrigeration cycles, in case of Rankine cycle, Rankine power cycle, we cannot follow the Carnot engine, whatever. Okay, now this is whatever. When we are talking about second law of thermodynamics, there only we have defined if it is the engine, then we have called it as the thermal efficiency. And then if it is refrigeration cycle, and then we have called it as COP, means coefficient of performance. Okay, and these formulas actually we have defined very well over there. Okay. Now, as like yesterday we have discussed, what is the ideal, whatever the ideal Rankine cycle was deviating and becoming actual cycle, the here also same philosophy is existing in case of vapor compression cycle also. Okay, that is because in the evaporator, more amount of heat may be it may be absorbing. Okay, that is based upon the room condition. Okay, or otherwise you are loading certain high temperature. I mean, otherwise so much of food stuff at a time in your refrigerator. Okay, so these two conditions. So your refrigerant, whatever the fluid we have in this cycle, we can call it as the refrigerant. Okay, there we in the Rankine cycle we have used it as steam, means water, and it is converting to the vapor, that is the steam. Here we have refrigerant. Different refrigerants we have. Okay, that slide actually in the next class I will show. In this class I have not included that actually. I have included, but where it's gone I don't know. Next class I will add that slide. What are the different refrigerants? Okay, anyhow, the working fluid we can call it here as refrigerant. Okay, that refrigerant may be entering over here in the superheated condition. Okay, like that way, this is deviating. Okay, and here in case of compressor, okay, heat losses from the compressor to the surroundings or from the surroundings to the compressor. Okay, both way can happen. Based upon that, it is deviating, its entropy is deviating in the condenser also. Moreover, what is this? As like your Rankine cycle, the heat losses and pressure losses because of the friction in the tubes. Okay, these all are dominating here and then making the actual means ideal cycle towards the actual cycle. In the refrigerator, suppose many tubings are there if you observe at the back. In case of your split AC, the outdoor unit is fixed outside and only evaporator is fixing inside. The both are connected by copper pipe, okay, and which is well insulated. Okay, what about that insulation? After some time, you can observe upon any AC, the insulation quality is deteriorating because it is in the sun all the time. Okay, means so also whatever those cracks and all can be the one reason to maximize or otherwise to increase the heat loss. So these are the things even in the evaporator how it is happening. So now based upon the requirement, okay, based upon the requirement and end user condition, this refrigeration system actually we can change. Okay, the pattern or otherwise configuration of the refrigeration system we can change. Here, this is one refrigeration system we have. We are using two compressors here. Okay, two compressors, and we will be using one mixing chamber. Okay, one mixing chamber. This we can use whenever the temperature difference is very much high. Okay, whenever the temperature difference. See here, this is 40 degrees centigrade. Here, minus 50 degrees centigrade. In case of our home refrigerator, if you consider, what is the minimum temperature we will be going? Probably -5 or -10. We just want ice, nothing more. That is also in the deep region. Yes. In the other cabin, whatever is the big cabin where you put just other food stuff. Okay. So that is even very low temperature means above the zero. Okay. So if you take even our air conditioning system, we will be able to put the temperature as 16. Means room temperature is not less than 16 or 15, like that we are, means we are setting the condition. Okay. Otherwise, some other applications, okay, some laboratory applications, or otherwise some other applications. If you see over here, the temperature difference is very much. Okay, the temperature difference is very much. Then you cannot compress whatever low temperature saturated this thing in one single stage to such a high temperature. Okay, in one single stage, it is not possible. That is the reason we have adapted over here two compressors. Fine. Why we are not able to compress in one single stage? See here. If you see, in case of your any compressor, which compressor? Air compressor, which you usually take pressure to your tires, cycle tire or otherwise scooter tire or car tire. Okay. In that mechanic shop, you might have seen this kind of compressor. Okay. So if you have not seen, now also you can observe somewhere here and there. If you observe that compressor unit, one big cylinder you can observe, another small cylinder you can observe. Okay. These two cylinders are connected by this kind of pipe. This pipe has many fins. That means thin plates are welded upon this pipe like this. Okay. So why this is required? These both might be connected to one particular motor only. Okay. See here. Let us assume here air is entering at atmospheric pressure, and here we are compressing to 12 bar pressure. Let us assume. Okay. Then when you are taking this much of air, okay, and then when you are compressing to 12 bar at a time, what will happen? Along with the pressure, your temperature also increasing. Okay, your temperature also increasing. So such a hot fluid, further you are handling and then passing to the storage unit means, okay, the air itself would be very hot, and handling the piping system also would be a problem. And along with that, if this compressor will be working for such a long time, then compressor wear and tears also would be very high. Okay. So in that view, what are we doing over here? This we can call low pressure cylinder. This we can call high pressure cylinder. Here, from the atmospheric pressure to some 6 bar pressure, let us assume. Okay. Some 6 bar pressure we are compressing. Then that air actually, whatever 6 bar pressure at certain high temperature is passing through this to the next cylinder. Okay. Meanwhile, what is happening? The pressure is constant because many number of fins are added over here. Okay. That heat is disposing to the environment. If you observe one more thing, behind this setup, there is one fan also. Okay. That fan also running by the motor. That fan sucking the heat from the environment and pushing upon this entire system. Okay. That way, the air while reaching over here will be 6 bar, but temperature is relatively decreased from here to here. Okay. Now, same amount of air is passing over here, that further compressing to the 12 bar, but whatever temperature is raised, that is acceptable range. Then this air going to the storage tank. Okay. That is the reason here we have this, we can call it as intercooler. Okay. This is actually, we can call it as normal intercooling or forced intercooling, we can call it. Okay. But in case of, if this kind of system is very big, oil cooled intercooler also there. Okay. Oil cooled intercooler. But anyhow, this is the concept I want to explain you, otherwise nothing. And here, one more thing. Why this cylinder is big, why this cylinder is small means, but the 12 bar means when you are sucking certain amount of mass or quantity at atmospheric pressure, that is some X. You are compressing to 6 bar. Okay, that volume is reduced. Okay, that reduced volume is coming over here. Okay, so that is the reason actually these both have certain volume relation. Otherwise, if you take again big cylinder, whatever you have compressed here, that is again expanding over here. There is no benefit. Okay, that's what all the time this cylinder is bigger, this cylinder is smaller. Both are connected with this kind of intercooler. If this is the small capacity compressor, then you will be having this whatever this air cooling type of intercooler. If capacity is very big, you will be having over here oil cooled, okay, intercooler. Okay, similar way. But here one thing you have to observe, whatever the air is entering over here, that is at atmospheric pressure and atmospheric temperature. Okay, here if you see this temperature is very low. This temperature to this temperature gradient is very high. Okay, very high. So if you connect these two, compressor 1 and compressor 2, by adapting this kind of intercooler, okay, that may not be functioning properly. Okay, that whatever small residence time passing from this compressor to this compressor is not sufficient to cool the mixer. Okay, not sufficient to cool the mixer. If you don't cool, what will happen? The load upon the condenser also will be increasing. Load upon condenser means you have to circulate so much of cold water over here, otherwise coolant over here. Okay, so that is the reason here we are taking one mixing chamber. Okay, and certain vapor we are mixing over here, that is getting cold, and then we are compressing in the second stage, and then cycle is happening like this. Very fine. Okay, and there is another very important configuration. This is the second type of configuration over here. And same like that in the previous condition. Okay, temperature difference, if you see, what is the temperature difference? 90 degrees. Okay, the temperature difference is 90 degrees. If you see over here, the temperature difference is 120 degrees here. This is minus 80 and this is minus 40. Okay, this temperature gradient is further increasing. In this case, actually, whatever the configuration we have seen over here, this may or may not be suitable for that this kind of condition. That's what are we doing over here? We are running two different systems of the air conditioning systems, or otherwise refrigeration systems we can call, two different refrigeration systems. This is one cycle starting from low temperature to the moderate temperature, and this is the another cycle working between moderate temperature to the high temperature. Okay, based upon that we have to select our refrigerants. Here if you see, this is R23, this is R410A. What are these? In the next class I'll add that slide and I'll explain. Okay, but what are we doing over here? These two are individual systems. Okay, working fluids, nowhere those working fluids are mixing. Only thing is, here you have evaporator. Okay, here you have evaporator. This is your cold space. Okay, this is your cold space. Then heat is absorbing over here, this refrigerant. And for this cycle, we need one condenser, right? Is it? This heat exchanger, whatever we are adapting over here, that is working as the condenser over here. Okay, that is working as the condenser for this cycle and the evaporator for this cycle. Okay, this is the simply one heat exchanger we can call. This heat exchanger functioning as condenser for lower cycle and evaporator for the upper cycle. Okay, so that way this kind of system we can call it as cascade refrigeration system. Okay, that is about vapor compression refrigeration system. Here apart from that, there is another concept. Okay, that is vapor absorption refrigeration system. Okay, that is simply absorption refrigeration system we can call. Here the working fluid is ammonia majorly. Ammonia has very good characteristics like at room temperature and at 10 bar pressure or more than that, the ammonia will be at the liquid stage. Okay, ammonia will be at liquid stage. If you reduce the pressure, even at the room temperature, okay, then that will be changing to the vapor form. Okay, vapor form. That means the fluid itself, if you will be able to change the temperature, okay, and pressure accordingly, then that itself is changing its phase and working as the refrigerant. Means cooling whatever the space you are designed. Okay, the same thing is happening over here. Here as like vapor compression system, here also we have, this is the condenser, this is the evaporator. Okay, this is your cold box, suppose. That's what here mentioned. And in between, obviously, you have seen what is the expansion valve is there. Okay, so suppose expansion valve means in your refrigerator, you might have seen one spring kind of coil, very long coil. Okay, that is very narrow tube. That is your expanding device. That is a capillary kind of tube. Okay, this is your expansion valve. This is condenser. This is evaporator. So what is happening over here? Whatever low pressure ammonia is coming over here, that is diluted, means what we can call it as means low intensity ammonia solution or weak solution will be there over here. This is absorbing this, and then this will be pumping through the heat exchanger, and it is reaching over here. Here what is happening? You will be giving certain heat over here. Okay, this is the heat supply, this is the heat rejection. Okay, so you will be supplying certain heat. Because of that, it is changing to the high pressure vapor. That vapor again condensing over here. Okay, and again the liquid is expanding in the capillary tube, and it is sucking. Since it is liquid stage, it is absorbing heat from your cold box, and that low pressure ammonia vapor is coming over here. Okay, and to the high pressure we are pumping like this. Okay, we are pumping back to the high pressure temperature. So based upon that, whatever the heats we are supplying, okay, this work input is what? Pump work input, as well as this one work input. Means work input means obviously energy supply. Certain quantity of work we are giving here to supply the, means to pump the liquid, and certain quantity of energy we are supplying here to heat it. Okay, that's what this is the total heat supply. Apart from that, efficiency based upon your COP, then you can calculate based upon the simple formula like this, whatever we are practicing from the beginning. Okay. So these are about phase changing power as well as refrigeration cycles. Apart from this, we have many cycles. Okay, in that the working fluid is not changing its phase. Okay, the working fluid is not changing its phase. Those we can call as air standard cycles. Okay, those we can call air standard cycles. Today, at least, let us cover a small topic. So, I have changed the slide to be able to see? I hope so, because I have shared my entire screen.
Yes,
But still, yeah, thank you. Now, similarly, we are defining certain cycles, both like power cycles as well as refrigeration cycles, where phase change is not happening. Okay, of the working fluid, phase change is not happening. Whatever your internal combustion engines, gas turbine engines, okay. So these all are coming in that. Okay, composition might be changing, but phase is changing. Suppose your internal combustion engine, you are sucking the air, you are leaving the pollutants. Okay, phase is both gas, nowhere it is coming to the liquid. Okay, even in petrol engine or diesel engine. Okay, like that. Today let us discuss about Brayton cycle, which is one important component in air standard power cycles. Usually, Brayton cycle is working cycle in case of gas turbine engines. These gas turbine engines, as you know, these are the engines in aircraft applications. Okay, your gas turbine engine is like this. Okay, if you broadly divide this we can call it as intake. Okay, intake. In an airport also, you can observe at front one big fan will be rotating. That only you will be able to see. Okay, when engine is running in the airport, okay, when you are boarding, you can see one fan kind of thing is rotating in front of the engine below the wing. Okay, that is only the intake. At the end, you can see one black color small nozzle kind of thing. That is only providing you this thrust. Apart from that, remaining all components are included or otherwise embedded in this particular casing. Okay. So, okay, anyhow, this is the intake. It is taking the air, means it is sucking the air, but it is not raising the pressure anyhow. Okay. So, what are those categories? Which is just taking the air but not raising the pressure? Your fan, whatever the fan you have right at your home, the fan is actually circulating the air, but pressure increment is nothing, very minimum. And even certain blowers, okay, delta P is very minimum, but quantity of air is very high. Okay, those kind of things are actually intake. Okay, this is the intake over here. Then after we have here compressor. Okay, this compressor is actually, if you see, the passage is area or cross-sectional area or passage is decreasing over here from here to here. Suppose m quantity of air is entering over here, the same m quantity of air is leaving over here. Okay, but cross-sectional area is changed. Okay, that way it is compressing. It is compressing to the high pressure. Then it is passing to the combustion chamber. This is your combustion chamber. We can call it as can combustor or dump combustor, whatever. Here certain amount of fuel is injecting, okay, and it is burning over. This whatever compression is there, that is again isentropic compression, okay, and whatever this combustion is there, that is constant pressure combustion, okay, that is constant pressure combustion. Then here we have turbine, okay, here we have turbine. This turbine is actually, we are extracting work by passing these hot gases upon the turbine blades, okay, upon the turbine blades. Now next one is the exhaust, that is the nozzle. Now based upon these two, based upon the turbine and exhaust nozzle, we can define the type of jet, this type of gas turbine engine. Suppose when this gas turbine engine is adapting upon your aircraft, what you need over there? You need thrust. Okay, because of the thrust only, your aircraft is able to move up or moving. Okay, here actually, whatever the energy we have, that maximum energy we are getting. Okay, some minimum amount of energy we are using upon this particular turbine. The energy which are extracting from the turbine is equal to whatever this compressor should run. Okay, that way we have coupled. Otherwise, maximum amount of gases are passing through the nozzle. This nozzle is generating the thrust. Because of thrust, your aircraft is moving. Okay, that is for gas turbine when you are applying upon your aircraft engine. Now, if you use this for your electric energy production, okay, if you use this for electrical energy production, as like your steam power plant. In case of India, we have coal and we have water. We are running and we are burning the coal and we are steam-based Rankine power cycle. we are extracting the electrical energy. Some countries like Gulf countries, okay, or Russia, they have so much of gaseous fuel resources. Yeah, somebody was asking something. Okay, if nothing, then please keep your mic in mute. Okay, so where actually they have gas resources. Okay, then for them actually this is the feasible solution. Okay, this is the feasible solution instead of going thermal power plant with the steam and boiler where so much of heat losses are there. Okay, so this is the solution. But in that case, if it is for the purpose of electric energy generation, okay, then no need of thrust. Thrust component 0. Yes, thrust component 0. In that case, maximum amount of energy, whatever energy producing in the combustion process, is utilizing upon the turbine to generate the electrical energy. Here, this particular turbine is connected to generator also. That generator is producing your electrical energy. Okay, this is about what is the gas turbine engine. Okay, what we have mentioned, this is isentropic compression, this is constant pressure combustion, this is isentropic expansion. Okay, let us see now. Let us see. This is our cycle. Here actually this is the open cycle, this is the closed cycle. Okay, so whatever this, when you are using for aircraft applications, that is open cycle. Why? Because you are expanding so much of amount of air, sorry, combustible gases through the nozzle, that is generating your thrust. Is it? So that's what this is your open cycle. The closed cycle. In case of land-based applications where you are generating electrical energy but not thrust, okay, there you can use this closed cycle. We have one heat exchanger over here. Okay, so whatever hot gases are coming up over here, those hot gases are passing. Okay, those hot gases are passing to the heat exchanger. Let us assume it is here. The whatever air passing over here, okay, whatever air passing over here, that will be heated over here. That means what is happening over here? Heat recirculation is happening. Okay, heat recirculation is happening. Because of that, thermal efficiency will be increased. Okay, thermal efficiency will be increased because these gases would be around 1400 Kelvin, 1500 Kelvin, like that. Okay, that much of huge energy potential is there, right? That potential is wasting over here. If you use heat exchanger, the air which is passing over here, that is not directly passing here, that is coming to the heat exchanger and interacting with this exhaust gases. Okay, both are not mixing. Both are mass mixing is not happening, only energy exchange. Okay, only energy exchange. What is the mass mixing? Suppose you have hot glass of milk, you want to make it cold. If you add certain amount of water in that directly in the glass itself, anyhow milk will be thin, but you will be able to drink it quickly. Its temperature is reducing. Okay, so obviously quantity is increasing, whatever amount of water you have mixed. Apart from that, there is another solution. Take your glass, go to certain water tub, insert in the water tub, ensure that it is not spilling in the water tub, just circulate by hand. You might have done many times. What you are doing over here, water and milk are not mixing. The boundary is the glass surface is the boundary. The heat from the milk is crossing the boundary of the glass surface and giving away to the water. Yes, the same principle if you have over here heat exchanger. Okay, the heat from the exhaust gases is giving to the cold air. After getting this heat, the cold air becoming hot, and that hot air is coming over here. Because of that, combustion performance, okay, will be increasing. Simultaneously, the heat, waste heat is minimizing. Okay, that is about this concept. Okay, So these are obviously, this is isentropic compression, this is isentropic expansion, this is the constant pressure. Obviously, this is also constant pressure. Further, these cycles PV diagram as well as TS diagram we have included over here. Okay, fine. Now, you know very well about this. Okay, efficiency is this much only, QH minus QL by QL means QH, because QH minus QL is the work output, QH is heat supply. Okay. Then this QL again, whatever we are taking in terms of the enthalpy, yes, where the QL is happening, heat rejection is happening in case of your heat exchanger. This cycle, whatever we are drawing over here, this cycle is for closed cycle actually, not open cycle. In case of open cycle, we don't have this. Okay, we don't have this line 1,4. So directly fresh air is entering here, compressing, heat addition, constant pressure heat addition, isentropic expansion, and going to the environment. And again, fresh air is entering over here, isentropic compression, constant pressure heat addition, isentropic expansion in the turbine. Okay, this line won't be there. When you are considering it as the closed cycle, then this is okay. So then whatever heat rejected QL is H4 minus H1. Whatever his heat addition, that is H3 minus H2. Okay, that we have added. Enthalpy is anyhow MCP delta T. In terms of that, we have changed this formula. These all are simple things, as you know. Then here, if you see the pressure ratio, because this is the constant pressure process, this is the constant pressure process. In between these two constant pressure lines, these two isentropic compression process, isentropic expansion process is happening. Okay, that means pressure ratios of P2 to P1, P3, P4, both are same. Yes, that we are putting. Okay, that assumption we are taking, and based upon your adiabatic process, whatever we have derived in our previous classes. Okay, the pressure and temperature relation is this. Those we are using, and your thermal efficiency is defined like this. Okay, this is thermal efficiency formula in terms of the pressure. Okay, in terms of P1, P2. Okay, thermal efficiency of Brayton cycle in terms of P1, P2 is 1 minus 1 by the ratio of P1, P2, K minus 1 by K. Okay, this you have to remember. Okay, so the thing is actually your exams are going to be offline exams. Okay, along with your mid exam and upcoming end exam. Yes, so please read all the concepts and remember appropriately. Once you understand the concept, you can easily remember all the formulas and all. Okay, so this is about Brayton cycle, but it is not completed. This is very lengthy. Okay, let us discuss tomorrow. Okay. Okay, then thank you. If you have any doubts or any questions, so please. One thing is actually somebody has asked me whether should we bring steam tables or not. We will be providing the steam tables. It is required, or upon all the computers we are going to install EES. Okay, EES, engineering equation solvers. We are going to install. Okay, that will be available over there. Okay, so since you have practiced very well how to solve the problem through EES without support of steam tables or any tables, property tables, so you can get these all properties through the EES. Okay. Okay.
Thank
So
you,
any
sir.
other? Yeah, please. Hello. Okay. Thank you. Bye bye.